In Part 2 of Lecture 11, we will discuss free space management and directory implementation. Files are not the only thing of which we need to keep track of in a file system. We also have to know how much free space we have and where it is within the file system. There are a few techniques that are used to do this, including bit vectors, linked lists, grouping, and counting. If we look at every block on a logical volume, we'll see that it is either in use or not in use. So this means that we can express its availability by means of a single bit per block. In this slide, you'll see an example of a bit vector. A 0 is used to indicate that a block is unavailable. It may be in use or it may be damaged. And a 1 indicates that it is available. Determining whether a block is in use means counting up to bit number n to determine if block n is available. This can generally be done quickly. All we need to do is find the first non-zero word or byte. The very fact that it is non-zero indicates that at least one of its bits is a 1. By multiplying the number of words or bytes that we have traversed by the number of bits per word or byte and then adding the bits offset, we can obtain the number of the available block. There is a downside to this. Using bit vectors slows things unless we can keep the entire thing in memory. And as disk drives get larger, this is increasingly impractical. A 2 gigabyte disk drive with 1 kilobyte blocks will require a bit vector of 262 kilobytes. However, clustering the blocks in groups of 4 or 8 will cut down the size of the bit vector. We can also use a linked list, similar to the way in which we use it to keep track of the blocks in a file. While traversing such a list may not be a simple matter, we would have to read each block from disk one at a time. Fortunately, this is not usually the case. We are usually looking for one additional block onto which to write data. One other advantage of the file allocation table approach: tracking free blocks is built in, so there is no additional accounting to keep track of. Imagine that we might actually need to be able to allocate several blocks at a time. We know that the linked list approach is not very efficient in this regard. But if we stored the addresses of a large number of blocks in a free block, we would need to read only one block to access a large number of free blocks. Frequently, the system will allocate or free several blocks that are contiguous. Sometimes this can just happen, but sometimes it is because we are using contiguous allocation. In either case, instead of recording the addresses of the blocks, we will simply record the first block's address and the number of contiguous blocks that are available. In any instances where free blocks are clustered, this will require much less memory to track them than if we wrote all their addresses individually. Directories are checked frequently. Every time we open a file, or copy it, or delete or perform most operations, we will need to access its directory entry. This means that the method of implementing directories will impact the file system's performance. The most obvious choices are a linked list or hash table. Linked lists offer a method of implementing a directory that allows directories to grow and shrink as necessary, and linear lists in particular are easy to implement. We can insert extra entries in the right place when we need them, and delete or reuse entries that are no longer needed when the occasion arises. The only downside to this is a significant one. Linear lists require a linear search, which becomes very slow when the directory gets large, while other list structures, such as binary trees or B-trees, can turn the search time into an order log n algorithm. It also makes the implementation of the list more complex. One alternative is to implement the directory as an array of records with a hash table as a search method. We can calculate the hash value h based on the name of the file. The hash table's entry number h contains the index of the file's directory entry, and now we can find the directory entry much more quickly than by any other method. There are two caveats that must be added to this. Firstly, we must pick the hash method carefully to minimize the chance of hash collision. Duplicate hash values are quite likely, and there must be some means of resolving the ambiguity that they present us with. Secondly, such a directory implementation implies that the directory is a static structure in size, and that means that we have an upper limit on the number of files that it can contain. In real life, this happens, albeit rarely in Windows, whose current version limits directories to 4 billion entries. There are many things that we can do in implementing a file system that make a big difference in terms of saving time or saving space. One example of this is that Unix pre-allocates storage for inodes when creating a disk partition. While it may seem wasteful that even a supposedly empty disk has a certain amount of its disk space used up, it improves file system performance in the long run. This will result in a file being stored near its inode location, resulting in shorter seek times. We will talk more about seek time shortly, and we'll see that it makes reading a file go much faster. Clustering schemes result in internal fragmentation, but at the same time it results in shorter seek times for files and in faster data transfer. When designing a file system, it is important to consider quite carefully what data should be written in the directory entry. The time and date of the last modification is routinely saved for files to ensure that we know which file to back up. Some other systems also save last time of access. Since this changes every time we access the file, we constantly have to update it. This can add to the number of disk write operations that need to be performed. File pointers are usually 16 or 32 bits in length, the standard word size on most computers. 16-bit pointers limit file length to 64 kilobytes. 32-bit pointers limit it to 4 gigabytes. While these may seem to place real limits on file size, the pointers are more easily manipulated than the 64-bit pointers used by some systems, which take up more space and make disk allocation methods and free space management methods also require more storage. Disk caching is based on the idea that the most recently read data blocks are more likely to be read in the immediate future than other data blocks. By storing them in memory and writing them at our convenience, we can access them more quickly than if we always had to go back to the disk to access their contents. RAM disks are a variation on disk caching. We treat an area of memory as if it were another disk drive. Programs can access it as they would any physical disk drive, with the only significant difference being the greater speed at which the data is read and written. One must remember that a RAM disk is volatile and thus can only be used to store data temporarily. While RAM disks are a lot like caches, the most important difference is that RAM disks are controlled by users, not by the operating system. You have to remember that computer data is not directly written on the disk. It is stored in cache and in buffers, and is written on disk as the system is able to do so. This means that in the event of a system crash, it is entirely possible that the data will be lost. Obviously, this is highly undesirable. Imagine that we have saved the records showing a sale, but lost the record of the credit card transaction that paid for it. We need some way to recognize when this happens and to fix it. Consistency checking involves comparing the data in the directory that shows what operations have occurred and what is actually stored on disk. If the directory shows that the file has been modified recently, but that this data is not in the file as recorded on disk, we have an inconsistency and the system will try to fix it. This is one topic that is generally covered in a course on database management systems. If you have ever accidentally deleted a file that you need, you know how important it is to save your data periodically so that you can retrieve it as necessary. And having an extra copy is always a good idea. System administrators, the people who run larger computer systems, and network administrators, the people who make sure that computer networks work properly, spend a lot of time overseeing backup operations. These operations are important in case data is lost in a system crash, if a disk is damaged, if a user accidentally deletes an important file. Backups are performed by saving data on magnetic tape or some similar archival medium. Backups can be done where every file on a file system is copied onto tape. This is called a full backup. Sometimes only files changed or created since the last full backup are copied. This is called an incremental backup. This is more frequently done than full backups because they can be done quickly. The reverse process, where files are copied onto the system after they have been lost or deleted, is called recovery. One can copy all the data on a file system onto tape. This is just files changed since the previous backup.